堂课哈 ，settle down, ladies and gentlemen. Okay. Today represent the last 3 lectures of this semester. Next week is the final. All right. Okay. Whenever I think that this is the last week that I need to teach for this semesters, I feel relaxing. I feel happy. Okay. Now I imagine you feel pretty much the same. Okay. Now, so as I said it several times, good things are ahead of you. Okay. Not just the winter section, but your entire future as a mechanical engineer, because technology has been improving rapidly, and the speed of improvement is not just fast but also accelerating. Okay, therefore we need better engineers more than ever. Okay, we need good engineers now. We need outstanding engineers in the future. Okay, I don't know what you want to do, and I cannot tell you what you need to do in the future, but I can tell you that this work always need good engineers. And if you want to step up, you want to go one step further, I can also tell you that this work also needs people who can lead research team. Okay, that is, we need research team leaders. Okay, especially engineering research team leaders. Okay, and typically those team leaders are being paid very, very well, but it's not that matters. Okay, it's the side product. The money you will get is the side product. The good thing about it is that you will receive a grade with some responsibility. You will receive you will have to face many challenges, but the payoff is that your work will be very creative. Okay, and you can have many important contributions to mankind. So I always said, the older I get, okay, the deeper I feel that being a good engineer is a very cool thing. To be a good engineer, very, very cool. Okay, all right. Let's go back to parameter variation. All right. Okay, large loop gain can reduce parameter variation, but it can also induce large overshoot and longer settling time, because large loop gain means that we make system respond more aggressively. Okay, and it will also make actuator saturation a problem. It will also reduce stability margin, especially in particular gain margin and phase margin, which is not good for the system, for the robustness of the system. Now, let's look at an example. The goal of this example is to demonstrate disturbance rejection. Okay, the capability, the disturbance rejection function of a feedback control system. Now, here, this represents the system we want to control, which is essentially a boring machine, and this is our controller. As you can see, it is a PD controller. This represents the proportional control, and this with the S, it represents the derivative control. All right. Now, here we have a unity feedback system. All right, and we have the nominal input here. We have the input disturbance here, and we know that from what we have just learned, the output should be this, okay? Not without parameter variation, without measurement noise, because the focus here is on how to reject input disturbance, okay? Reject is the term we use in control technology, okay? When we talk about minimizing the effect of input disturbance, we say we want to reject disturbance, all right? So let's first look at this transfer function, okay? Now, the equation is here. All we need to do is substitute every required terms into this representation. GC is nothing but K plus 11S. G is, of course, 1 over X times S plus 1, okay? And we can do the same thing to the denominator, okay? To make things look cleaner, we multiply everything, including the denominator and the denominator and the numerator by S times X plus, X times X plus 1. Then this go away, all right? Then the numerator will look like this. And similarly, the denominator, by multiplying the denominator by X times S plus 1, this term become this. And this term, because these two terms cancel each other, what we left is this, all right? So let me just rewrite this denominator as this. All I need to do is find the product of these two terms, all right? So this represents a transfer function from R to Y, all right? Now, I can do the same thing to this transfer function, all right? So that exactly what we are doing in this equation, all right? So I don't want to repeat the TDMS. Here, I just tell you that by using the same mathematical technique for getting this result, the transfer function between the disturbance and output is this. So by putting them together, okay, the final output is this plus this. Remember that this term comes from here. And this, this term comes from here, okay? So this represents the overall output of the system. When I say overall, I mean it represents the contributions. I mean the output comes from two sources. The first is the contribution from the nominal input. The other is the contribution from the disturbance. Apparently, this term is undesirable. This term is something we want to do without. We want to reject, all right? So, and then by definition, we know that arrow is defined as, arrow is defined as this. So based on this very definition, I can represent arrow as this, okay? We derived this equation in the last lecture, right? So let's just ignore this term for the time being. And I already know what is this, and I also know what this term is. So, for example, did I do that? Well, probably not. No, I'm sorry, I didn't do that. Okay, let's just take care of this term first. Okay, what is this term? Okay, let's just derive it term by term. Okay, now GC, of course, again is K plus 11S, and G is again 1 over X times S plus 1, all right? So if I multiply the denominator, the numerator and the denominator by x plus s plus 1, this is what I will get. And let me rearrange this representation to make it clear. Then this is the representation. Then I will get the final representation for this transfer function. And remember, this is the transfer function between the nominal input and the output arrow. Okay, so the output arrow now is another output. Okay, the actual output is an output. Output arrow can also be viewed as an output. In doing that, I want to understand the dynamics between the nominal input and the output arrow. Okay, to do that, I need to know what this transfer function is all about. Okay, and that's what I get here. Now the next part is we want to go to time domain. After all, when it comes to arrow, what really matters is in time domain, especially steady state arrow. Okay, now that is when time goes to infinity. What is the output of my system? How far away it still is from the desired output. All right, to do that, what we need to do is to use the final value theorems, right? Final value theorems tell us that whenever you want to determine in the steady state arrow, all you need to do, that means this is the output arrow. Okay, when we want to know steady state arrow, that is ESS. This t, that is the time variable, its value has to approach to infinity. Okay, according to final value theories, this equal to x approach 0, x times x of e of x. Okay, well, e of x is of course the Laplace transform of e of t. All right, so let's, by applying this final value theorems, this is what I will get. Okay, now remember, we are now in studying this term. Okay, now here let's assume what I have is a step input. All right, 1 over s step input. All right, so if this is the case, then these two terms can cancel out, and with x equal to 0, the denominators become k, and the numerator become 0, right? Because I have an x here. Whatever s multiply, when you multiply 0 with whatever number you have, it will always come out with a 0. Okay, so for this part, that is for the part associated with the nominal input, the corresponding steady state arrow component for this PD control system is actually 0. All right, now there is another factor we need to consider, that is input disturbance. All right, so let's just figure out what a transfer function is. Actually, we have, I believe we have done that before this. Am I right? Yep. Okay, this is this, right? So this is what I get for this transfer function, the transfer function between the input disturbance and its output arrow contribution. Again, I need to know the steady state arrow in the time domain. So let me apply the final value theorem again. All right, here I also assume TD to be a unit step function. All right, so its Laplace transform is 1 over s. Again, these two terms cancel out. And by making x approach 0, the final steady state errors is actually 1 over k. So to more effectively reject input disturbance, what I can do is increase k, all right? Increase the gain of the P controller. PD controller, the D controller, the derivative controller cannot do anything about the steady state error, at least not in this particular example, all right? Okay. Now, why does derivative control doesn't matter in reducing the steady state error? Because let's assume that you have a system, okay? Now, the desired response is here. Now, after applying the PD controller, the output become this. So when t approach infinity, you have a constant steady state error, okay? Now, this arrow is then fed to the PD controller, Kp plus Kds. And then this controller generates an action, all right? Now, if ESS is a constant, if you take derivative of this constant, it will produce 0. So in this regard, it is easy to see the derivative feedback cannot do anything about the constant steady state error because it is a constant. You take the derivative, what you will get? You will get is changing rate. But since it is a constant, its changing rate is 0. Therefore, derivative control cannot do anything when it comes to reducing the steady state error, right? However, if you increase Kp, it will matters because by increasing the value of Kp, that is by increase the magnitude of the proportional control, you will produce a more aggressive, a stronger, a corrected input, corrected force to the process, all right? Now, let's look at the results. Now, in this one figure, I will show two responses. One come from here, the other come from here, okay? That is one response due to the nominal input. The other is the response, the contribution of TD to the output, okay? Now, this is the state response YT, which is this blue curve. As you will see that it has 0 steady state error, just as we expected, all right? However, for this part, we want to know disturbance response, okay? And the disturbance response actually looks like this. Please pay attention to the fact that here, the numbers have different scales. Here, the number, when it comes with a unit of degree, comes between 0 and 1.5. However, for the disturbance response, the unit is still degree, but its magnitude, its amplitude comes between 0 and 0.015, okay? So the contribution, when it comes to the output, the contribution of disturbance is actually much smaller than the contribution of the nominal input. And that's good, all right? Because we don't want large error due to the disturbance. All right. All right. So let's look at another. Let's look deeper, okay, about the steady state error. Okay. Now here, I will assume that there will be no uncertainties whatsoever, which means the input disturbance does not exist. Parameter variation completely disappear, and I have perfect output measurements, which means zero measurement noise. All right. So the only output error I have is this term, that is the output error associated with the nominal input. All right. Now, why do we want to do that? Because the thing is that we want to know how to design a controller, what kind of specifications that a controller need to satisfy in order to reduce or even to minimize this output error. Okay. Now, so the only output error we need to consider is this. Okay. As I said it before, when it comes to output error, eventually we have to go back to the time domain. So we need to apply the final value theorems, okay, that is to determine the so-called steady state error. All right. Now, since the E of X is this, all right, this is my E of X. Okay, so I will use this representation to help me determine the steady state error. Now, one major assumption. Here, I will assume my loop transfer function can be written in this so-called general form, okay? Which means here, Zi and Pk can be real numbers. They can also be complex numbers. But if they are complex numbers, they have to come in pairs. That is, we always need to have a pair of complex conjugate numbers. In the real world, complex numbers always appear in pairs. No exception. Okay. All right. Here, I assume I have m zeros. I have q poles. All right. And an additional special term is this. That is, I assume I can have n pole located at the origin. That is, I can have m poles with x equal to 0. Okay. Remember, this is the pole for the loop transfer function, not the pole for the feedback control system. Because if I have pole located at here for feedback control loop system, that means the system is what? Marginally stable, which is highly undesirable, okay? Because we always want system not just to be stable, okay, but stable enough. And marginally stable is just not good enough for real feedback control system, all right? So remember, this is for loop transfer function. Closed loop transfer function is another story, all right? Okay, now here, n represent the type number of the system, okay? Type number. And in the following discussions, the focus will be on the impacts of n, okay? That is the time number of the loop transfer function. I will investigate what will happen when the value of n increases from 0 to 1. n to 2, okay? And if necessary, I can go even higher, okay? Now, let me do this one step at a time, okay? Now, here, I will study the steady state arrows from two different directions. The first direction is I will apply different inputs to the system. The first input is, of course, state input, but I can also apply rain input. And finally, I will apply acceleration input, which look like this. So there are three types of inputs. Why do I want to do that? Because I want to increase the difficulty of tracking, all right? Because step input represent a fixed target when it comes to control. It is nothing but a set point tracking, set point regulation problem. The target is always sitting there. So you want to hit that target. It is relatively easy because it's not, it won't go anywhere. It just is, it is there always, all right? However, if you have a rain input, which means the desired output is this, okay? It always increase with time. Then what you have is what? Is a moving target. So it is, the challenge of feedback control, of course, become more difficult, okay? All right? Now, if we step up, if you want to make things even harder, you change the input to what we call acceleration input or parabolic input, which means the desired output look like this. It means it is not just a moving target, but the movement of that target is actually accelerating, okay? And it becomes more challenging, okay? Now, the faster my desired output is, the more difficult to reduce my steady state error, because following a moving target, especially an accelerating moving target, is much more challenging than reach a fixed target. All right? All right. Now, that's the first direction. I will using different inputs to test the system. Now, the second direction is I will study system with different time number. Okay, time number 1, or time number 0, time number 1, and time number 2. Now, and I will show you that by increasing the value of time number, we can actually improve the steady state error. We can actually improve the performance of the system when it comes to steady state error. Now, let's first focus on the simplest case. That is, I have a state input. Remember that we want to use this equation to help us determine steady state error, right? Now, here, for state input, R of X is actually A of X, all right? For a unit step response, its Laplace transform is 1 over X. But let's just assume my unit step response, my unit step function has an amplitude of 8, okay? So by setting X equal to infinitely, equal to 0, okay? Remember that for the numerator, these two X will cancel out, all right? This is what I will get for the steady state error in the X domain. Now, remember that we assume the loop transfer function looks something like this. Now, since this particular slice assume time number to be 0, therefore, M here in this particular case is 0. All right? If that is the case, then this loop transfer function will become this. Why? Because N is 0, right? Then x to 0 is of course 1, all right? What we left is, what we left is this. But here, the requirement is that x has to be 0. So all this s go away, and we end up with this. Let's just assume this to be Kp, okay? Let's just define this as Kp. And this Kp has a name, which we call position error constant, all right? And it is actually, you know that from the about derivation, you know this is actually this, and this is actually this, all right? And since this is Kp, that means the position error constant is actually this, all right? All right? So how do I reduce this steady state error? I make Kp larger, okay? How do I make Kp, that is the position error constant, larger? I need larger loop transfer function DC gain, all right? Think of it as L, which means I need L, the loop transfer function, to be larger when S is equal to 0. When S is equal to 0, we are talking about DC gain, right? Okay. Now, so it makes sense, okay, but because the conclusion that we are getting is it is in good agreement with from what we studied in the last lecture, okay? Now, let's increase the time number, okay? Here, n is equal to 0. Let's now assume x is larger than 0, okay? 1, 2, whatever, okay, okay? And let's see what happened, okay? If that's the case, okay, what happened is that this, remember, this is my steady state error, okay? Now, here, originally, it looked like this, all right? Okay. Remember, what I have here is this, right? So I need to, in the denominator, I have the product of GC times G, all right? Now, also remember that X has to go to 0. So this thing go away naturally, okay? Now, let's keep this term, X to the n, okay? So if this is the case, then this steady state error representation can be rewritten as this. Now, to make things look cleaner, I times the numerator as well as the denominator by x to n. So by doing that, the numerator become this, and the denominator, because I cancel out these two terms, therefore this term become this. And by multiplying 1 with x to n, I have this term, all right? Now, the cool thing is because x need to be 0, so this disappear. And the denominator is this constant. But the important thing is that numerator become 0, right? So whenever n is larger than 1, that is, whenever the time number is larger or equal to 1, I will have 0 steady state error in dealing with step input, okay? So increasing the time number is really helpful because it reduces the steady state error from this to this, okay? And this is good because it can quickly eliminate the steady state error, okay? You cannot ask for more. Now, let's increase the difficulty of the challenge. Let's make the input the range input, which is, of course, a moving target. Again, I know that the error function is this. Again, let me apply the final value theorems to determine the steady state value. In this case, because I have a range input, therefore R of X now become A over X squared. Okay, now this is nothing but a rewritten representation of this. Okay, now what I need to do next is I multiply the denominator as well as the numerator by S. And this 2x, 2s cancel out this x squared, all right? And when you times s with 1, you will get this term. And when you tie these two terms together, this is what you will get, all right? So let me rearrange everything, okay? With s equal to 0, this term go away completely. And this is what I end up with, okay? Now remember, I assume the root transfer function to be this general form, okay? Now, let me rewrite this representation. Not rewrite, let's just move this representation here. Remember that that's what I get for the steady state error for the, when system is facing a range input, okay? Now, remember this is our assumption for the root transfer function. Now, when n equal to 0, okay? When n equal to 0, all right? What we will have is this become 1. And this s will always go away. So this become a number. Whatever that number is, doesn't matter. The only thing we need to know is that when n equal to 0, this term become 1. And therefore, GC of 0 times G of 0 become a certain number. But it doesn't matter because when it is a particular number, but this s is 0, then the denominator, the value of the denominator will be 0. And ESS in this case will become A divided by 0. And it therefore become infinitely large. So for n equal to 0, the steady state error is infinite. The system actually explode. The system never catch up, okay? And the error just become larger and larger as time progresses. And eventually it become infinitely large. And that is something, of course, not nice, all right? But this problem can be fixed. All I need to do is increase the type number, okay? Let's assume n is no longer 0, but 1, okay? If this is the case, then this additional s, okay? Remember here, this additional s, which can come from here, this additional x will cancel out this s, which is the s here, all right? Okay, think of, I have here, this is this term, okay? if n is equal to 1, then xn become s. And this x will cancel out this x. As a result, the denominator of the steady state error representation is no longer 0, but a fixed number. And this fixed number is what we call velocity error constant, okay? And it is actually this term, okay? The denominator of here, the denominator of this representation. Note that please be aware of the similarity between this representation and this representation, okay? This is the position error constant. It is the product of GC and G, all right? And for the velocity error constant, I still have the product of GC times G. The only difference is that there is an additional term here, that is S, okay? And by introducing this additional term into the multiplication process, I have a velocity error constant. And the steady state error, in this case, when n equal to 1, is actually A divided by KV. Same thing happened here. That is, for the same input, if I want to reduce steady state error when time number is 0, I need to increase position error constant. Now, for the range input, okay, when time numbers is equal to 1, when I want to reduce the steady state error, I need to increase the value of the velocity error constant, okay? So the way we deal with these two inputs are actually very, very similar. The only difference is that when the input become more complex, we need to increase the time number, okay? I will explain why increasing time number can produce such a positive result. Okay, let's step up, okay? Let's make the control problem even more challenging by using acceleration input, okay? So acceleration input means that the desired output is this. So you can see it is not just a moving target, it's moving speed. It actually increases with time because what we have is t squared. Now, if this is the case, its Laplace transform will look like this. By using the same mathematical techniques, I can write out the steady state error as this. This time, I will multiply the numerator and the denominator by x squared. So these three terms will cancel out with one another, okay? And with x, and I will time 1 with x squared, okay? And since x approaches to 0, this term I can just drop out this term. So what I have, what is left for the denominator is this, all right? Is this, okay? Now, this can be a problem because when x approaches 0, this denominator can have a value of 0 and it will explode, which means that we will have infinitely large steady state error. The only way to avoid this unfavorable situation is that somehow this s squared term can be taken away, all right? How do I do that? Let me examine what can I do for the loop transfer function. Remember, loop transfer function looks something like this. if the time number is 2, then this x squared will cancel out this x. So if that is the case, then this steady state arrow will look something like this. Well, the denominator here is defined as the acceleration arrow constant. All right, this is the acceleration arrow constant. So let me summarize all the results that we just presented. Okay, remember that what we are studying is the output arrow due to nominal input. Okay, here we do not consider any uncertainty. We assume zero input disturbance. We assume there is no parameter variation whatsoever. We assume perfect measurement, no measurement error whatsoever. All right. So for this part is different time number. Okay, in the horizontal axis, in the vertical axis. In the horizontal axis, what we are seeing is for different columns, we have different input. Here, state input. The next column, rate input, and then parabolic input, which is acceleration input. Okay, the content of these 3x3 tables is actually steady state arrow. Okay, when time number is 0, when facing for a time number 0 system, when facing a step input, this is the steady state arrow. But for such a time 0 system, if you wanted to deal with random input or parabolic acceleration input, you will get what? You will get infinitely large steady state arrow. Okay, if you want to make this, improve this situation, what you can do is increase the time number, and the arrow, steady state arrow, will be reduced to Ka over Kv. And if you want to go one step further, just increase the time number again. Now increase it from 1 to 2, and then you have 0 steady state arrow. So everything we have done for studying steady state arrow due to the nominal input are summarized in this table. Okay, now why time numbers matters? Where is the magic of time number come from? Remember, time number actually represent S in the denominator, and it represents integral action. When time numbers is equal to 1, which means you integrate the arrow once. When the time number is 2, it means this, you integrate the arrow twice. In calculus, we call that double integral. When time, okay, so you can perform single integral. You can also perform double integral, okay? So in the integral component in a controller, such as PI or PID controller, what does it do? It calculates its output based on the accumulation of the output of arrow over time, okay? So integral control actually consider the history of the output, because after all, it accounts for the accumulation of the arrow over time. And that is what result in a so-called driving arrow to 0 action, all right? Okay, let's take a 10 minutes break.